All right, let's review the assumptions for our two confidence intervals. They're going to be a one sample z interval for the mean and a one sample t interval for the mean. But the conditions are basically the same as the conditions for the sampling distribution of x bar that we learned in the sampling distribution chapter. First, you got to have a random sample or a randomized experiment. Again, we're going to talk about these experiments later, so don't worry about that. Fill in the reason for each check. The reason is, so x bar is unbiased. And that's for the center, right? So it's centered. So my x bars are centered about the true population mean. Most important thing. 10% condition, same as before. Why is it important? So sigma over square root of n is good enough because of independence or pseudo-independence, whatever. Therefore, s over square root of n may be good enough after the t correction. And then normal large sample says, so the way this check is actually going to play out differently, and we're going to spend some time working on this check. So if you remember, it was first check the original distribution. If the original distribution is normal, then you're good for all sample sizes. If the original distribution is not normal, then your sample size needs to be big enough, and we said 30 was the magic number, even though it's really not. I mean, it's okay. But here's the thing. The mean, the population mean is unknown. Population standard deviation is unknown. The population shape is also going to be unknown. I mean, how often do we know the population shape? Never. So here's what we do. If the shape of the population is unknown and your sample size is small, then we need to analyze the shape of the distribution of the sample to assess normality of the population shape. That should make sense, right? We look at the sample data. If the sample data looks normal, then the population it came from is probably normal. If the sample has outliers or shows strong skewness, then the condition is not satisfied. So that should all sound good in theory, but here's the thing. Your sample data is never going to look normal, and for small sample sizes, even this is going to be kind of questionable. I'm contemplating whether, in class I talked about it and we went on and on about it. We should talk about it in the video too. Let's cover all the bases. First of all, we're going to use the check, and the check is fine. I just want to talk to you about how ridiculous the check is. So let's say these are our populations. We're sampling from two populations. This one's normal, and this one is strongly skewed to the right. Okay? And let's say we're taking samples of size, well, first let's just take a quick little sample of size 20 or 30. I mean, decently sized, but under 30. If you're sampling from a normal population, there's a good chance that you're going to get a nice collection of, you got 20 points. Maybe it's not going to look normal, but it should look symmetric and without any outliers. Should. And if you grab it from this one, there's a good chance that you're going to get most of them in here, but you might get one up here, right? This is kind of what we're hoping to see. An outlier here to give us an indication that the population distribution is skewed, so we can fail the check. And if we get this, then we're good. But, think about whenever you have a sample of size 4. So best case scenario, the way it's supposed to work out, you get a value here, a value here, value here, and a value here. That looks symmetric with no outliers. Value here, value here, value here, value here. Skewed. Fail the check here, pass the check there. But you have to realize that it is entirely possible that you get a value from here, here, and here, and a value from here. And if we see this in a sample, we're going to say, look at this outlier. I bet you this didn't come from a normal distribution when it actually did. Or we are over here and we get a value here, value here, value here, and a value here. And we're like, oh, this is good. No outliers, approximately symmetric, so we're going to pass a check. There's no getting around this. I'm just pointing out to you that it's a problem. You cannot assess the shape of a population by looking at a distribution of 4 data points. You can't even do it with the 20. Even when we had the 20 data points here. We could get one of these crazy values out here for our 20th value, and we got 19 here. And we're going to fail this check when we shouldn't have. Similarly, sometimes we're going to pass the check when we shouldn't. So this check isn't very effective. But there's not much we can do about it. So we just run it. If the sample has outliers or shows skewness, we're going to say it came from a population that was skewed, and it's going to fail the check if the sample size is small. The one thing we do have going for us, though, is this idea of robustness of T procedures. So let me give you a definition here. The definition of robust in statistics. A statistical method is said to be robust with respect to a particular assumption if it performs adequately even when that assumption is violated. So what does that mean? That means if you fail a check, the procedure is still pretty effective. What do we mean by pretty effective? Well, if it's effective, our 95% confidence interval is capturing 95% of the time. That would be effective. If it wasn't being effective, then it's going to maybe capture 80%, or it's not going to be right. It's going to capture less probably. So these T procedures they perform adequate. Okay, I'm sorry. Read this sentence here. Procedures with sample means using the T distribution are robust with respect to the normality check, the third check. But we should still note if the condition fails. So what this is saying is these procedures are pretty good when you fail the third check. So yeah, it's not going to be 95% effective, but maybe it'll be 93%, or maybe not too bad. Maybe 92, maybe 94. I don't know. But they're going to be close to as advertised. Whereas nothing is robust with respect to the random check. If you fail the random check, you're screwed pretty much, right? So this kind of should make you feel maybe a little bit better about how bad this check is as far as doing its job. Regardless, all of this is kind of moot for AP Stats. In AP Stats, we run the check as it is here, and that's it. By the way, if you ever fail a condition on the test, if it says to do a confidence interval, you have to do the confidence interval. Don't say that since the check failed, I'm not going to do the confidence interval. Do the confidence interval, and if you fail the check, make a note at the end, maybe saying, but this check failed, so maybe it might not work 95% of the time. All right, so because this third check's a little bit different, let's do a couple of examples. GPA, coffee, and actually I don't think this is GPA. Whatever. Determine whether the third condition for a one sample T interval or Z interval for mu are met. We want to estimate the average wait time to order a regular coffee at a local coffee shop, your local Starbucks. The time for 5 randomly selected visits at a local coffee shop are shown below. So we're just running the third check, the normal large sample. So I don't know the shape of the population. I never will. So we don't really start with that. Start with the sample size. N equals 5 is less than 30. Okay, so we don't qualify for this one, for the large sample portion. Well, let's take a look at our sample data and see if we can say that the original distribution is normal. Well, I see these 4, and then I see this outlier. Looks like it's skewed, not symmetric with an outlier. So I say the sample data has an outlier. So this is kind of the optional statement. Therefore, the population data, the population distribution is likely skewed. And if the population distribution is likely skewed, then this fails. Therefore, the sampling distribution of X bar may not be normal. Not sure, but probably not. So this check fails. But, we'd still do the interval if they asked us to, but our interval wouldn't be very reliable. Part B, we want to estimate the average height of students. Box plot below shows their height and of 100 randomly selected students. So first of all, looking at the data set, I see some outliers. We wouldn't be too concerned with these outliers because there's kind of one on each side. Mostly we're concerned with skewness, but let's just run the check. Normal, large sample. Check the sample size. 100 is greater than or equal to 30. Boom. If your sample size is big, we don't even need to look at the graph at all. Doesn't matter if there's outliers or skewness or what it looks like at all. The condition checks. Therefore, the sampling distribution of X bar is approximately normal. And yes, you need all of this. Third example, normal, large sample. Middle school counselor wants to see if kids on average, or how much time kids are spending on average on homework. Histogram of the amount of time spent on the previous evening for a random sample of 20 kids. So n equals 20 is less than 30. Okay, so we're not large. So let's take a look at the data set. See, don't expect this to look normal. Data is not going to look normal. What we're looking for is evidence that it came from a distribution that was strongly skewed. Well, there's no outliers, and it's approximate. So the data, the sample data, is approximately symmetric with no outliers. Therefore, the sampling distribution of X bar is approximately normal. So the check checks out. Okay? Now we're ready to actually do a confidence interval. 1 confidence interval, 2 confidence interval, and some sample size stuff. All right, it's probably going to be 2 or 3 more videos though, sorry.